close the system. How does this work? Here we have the temperature. How can we connect the temperature? Omega is okay, so we have omega, so we can try to replace that somehow here. But then essentially we have two equations here, but three unknowns. The stream function, omega, and the temperature. So how do we proceed? Do you have any suggestions? VG? We need to find a solution for the temperature field. What can we use for the temperature field? Do you have any ideas? We are very lucky because we have the hydrostatic equation. Because the hydrostatic equation tells us that d phi by dp is equal to minus r t over t. And phi, our phi field is related, we know that phi field is related to the stream function by just, it's just f naught times the stream function. So here we have directly already the stream function, our stream function included. So we can use this trick here. We can replace the temperature by the stream function. Only that the problem now is indeed vertical derivatives become important. Whereas before, there was no vertical derivative in all these operators because all our Laplacian and so on advection terms were horizontal operators. But now a vertical operator becomes important. So we can replace this here in this equation and get to the two equations that so you resolve this for t. T is equal to minus p over r d phi by dp, and insert that in that equation. There we are. So that gives us this set of equations. And now the system is in principle closed. We don't know yet if we can solve it, but in principle it's a closed set of partial differential equations. Because we have two equations. One is related to the vorticity, the other is related to the energy equation, as we have discovered. And two variables. One is the stream function, the other is omega. All other fields we assume to be given as a parameter. F naught, sigma, the stability, we assume to be given by some kind of reference stability field. So everything else we know. So in principle we can solve this problem. So we have this and this equation. This is the thermodynamic equation related to where we replace the temperature through the hydrostatic equation with the geopotential and then with the stream function according to this equation. So this is our coupled set of equations. In principle, this can be solved as a three-dimensional problem now. But it's quite complicated. So we use a slightly different and easier approach, less complicated in the mathematical treatment, even though the calculations are in the end still quite tedious. But in principle, we make the problem slightly simpler compared to this three-dimensional problem, because now we should really look for waves that in principle can also propagate vertically. But we use a simplification here, which is the following. We discretize these equations. You have experience with this already from your numerical methods course, of course. But this is an extremely crude discretization. So we use essentially 4 pressure levels. So 1, 2, 3, 4. The upper level is 0, the lower level is called 4. And omega from 0 is assumed to be 0, and omega from 4 is assumed to be 0. So 0 velocities at the boundaries of our system, but in between there can be omega different from 0. So omega will be defined, so this is labeled, I've forgotten one level. Omega is defined at the even levels. And this is usually not. So omega we only have to consider essentially at the mid-level. And in this uneven levels we consider the stream function. So we call this in numerical methods a staggered grid. One variable is defined at even grid points, the other variable is defined in between. We can say we have only 2 levels, and then the staggering is done here by kind of doubling the number of grid points. So the stream function we would define in these 2 levels. That's our trick. The trick becomes actually clear why we want to do this. And now we want to of course then derive an equation for the stream function at this level and at this level, and for omega at this level, and see if we can close the system. Then we have eliminated the vertical direction because we have used the discretization of our system. So the vertical derivatives we want to discretize using this kind of system, and we assume that this distance here is 500 hectopascal. That's the number that we will use. So the same distance as this. 500 hectopascal would be the delta P that we are using here. So the first thing we observe then that our dW by dP, the change of the omega with these boundary conditions. Now, if we want to know what is that, we have to pose the vorticity equation at this level. But at this level, then we have to know what is the vertical derivative of the vertical velocity at this level. But we don't know. The vertical velocity at this level is not defined. So we have to use the omega field at the other levels. So if we want to know what is the vertical derivative of the vertical velocity at level 1, we could estimate that by the vertical velocity at level 2 minus vertical velocity at level 0 divided by the pressure difference delta P. And since this is 0, this is just omega 2 over delta P. The same is true for the vertical derivative here, if we apply this equation at level 3. So with that, our vorticity equation applied to these two levels look like this. We only indicate the level by the number 1 here, and the level 3 by the number 3, and then this just changes sign. Okay, so here, so far, it was quite easy to use this trick to get rid of the vertical coordinate in our problem. The vertical changes will still be important, but they are just now expressed by the change between psi 1 and psi 3, so very much simplified with respect to a real three-dimensional problem. In the thermodynamic equation, we want to apply the thermodynamic equation at this level here, but then we have to express the change, the vertical change of stream function, which now we can express as the stream function at level 3 minus the stream function at level 1 divided by the pressure difference. Again, same difference, 500 hectopascal here. All these are equal spaced in pressure. So we do this and multiply this by delta P, the constant pressure difference, which is another parameter now in our system, but this is given. We have defined this to be the case, 500 hectopascal. And then this is the equation that we get. So in principle now with this we have simplified our system grossly. Now it's true that we have one more equation. We have 3 equations instead of 2. But they are only, we have only to solve them in the 2 dimensions, plus time, of course, but not in the vertical direction, because the vertical direction has been discretized. So now, in principle, we have a closed system of 3 equations for 3 variables. The only variables that appear here are psi 1, psi 3, and omega 2. 3 equations for 3 variables. So in principle, we should be able to solve this. Of course, these are still partial differential equations. So we have to do something more.
Professor?
Yes?
Excuse me. How can you imagine that this solution will work? I mean, who is the first guy that invented this trick, and why?
This is called ED model. Yeah. Why? I think the answer to many of these is difficult to say. I don't know. I guess the answer is that in the end, you're right. It's a crude approximation to the problem. The real atmosphere we divide into just a few levels that are able to represent the fact that our waves can vary in the vertical direction, and we have the chance to express our mean state with changing in the vertical direction. So this is really the zero order model that can be posed to solve this problem. As I mentioned before, one can solve the 3-dimensional problem, and this is also done in some textbooks. I find this simpler approach more illuminating because the parameters are so easy to interpret in terms of this discretization that I quite like it. And in the end, I think what is important is that that the results can be compared well with observed growth of baroclinic waves. The results are very intuitive and can be, if you analyze, I don't know, weather maps, they may be corresponding to what we see as typical growth properties of baroclinic waves in the observations. But yes, this is a very crude approach. But the same is true for Rossby waves in principle, where we assume, okay, we have a...
But so basically we exchange our variable, we set more boundary conditions at more vertical levels instead of having variability.
What? I mean, these two boundary conditions are often applied. This is no problem, because our top in models is really the pressure vertical velocity and the pressure itself. At the top level we could set to 0 for an idealized model. No problem there. This is a problem, because in reality the vertical velocity and pressure, the vertical velocity in real space, if we don't have orography, would be 0. But the vertical velocity in pressure coordinate system cannot be set exactly to 0. It turns out it's quite a good assumption to do this. But it's not exact. This is, for example, not exact. So the only boundary conditions we impose are these two. The rest is just a discretization, a crude discretization of our system. We could, of course, use more levels. But then instead of having a 3-dimensional system to solve, we would have a whatever dimensional system you decide. 20, could be 20-dimensional or 10, depends. It turns out that there are models, actually even numerical models, that work quite well on very few vertical levels. The only thing you really have to represent is the fact that your systems can change in the vertical direction. You have to allow that this is possible. Otherwise you have a barotropic model and you go back to the problem that we had before, if nothing changes in the vertical direction. So I would say it's a very crude approach, but justified by what we can learn from it.
It's like if we divide into domains, and we solve separately,
yes.
And then we set the boundary.
Well, it's coupled, right? These two equations are coupled through the thermodynamic equation. It's not that they are uncoupled. If they were uncoupled, it's trivial, but it's not the case. So if you look at these two equations, the uncoupled case would be the case where we don't have vertical velocity. Then we solve them independently. We may even say they have different advection velocities, but they never talk to each other. Then it's a trivial problem. We have not gained anything. But the point is that these two levels are coupled by the vertical velocity. So that makes this system interesting. And to kind of close the system, then we have to use the thermodynamic equation, which we have used. Yes, it's crude, but I think we can learn a lot of things still by solving this in this very crude way. Everything we've done so far is quite crude, huh? So don't. But I think it's a good way to attack this problem, because baroclinic instability is quite a tough problem if you do it in the 3-dimensional space. But as I mentioned before, it can be done, but it's more complicated. So in principle, within the assumptions that we have made, this is still exact. Okay, it's a crude discretization. Maybe we are not happy with the fact that our model has only 2 levels in principle in the atmosphere. So it's a crude discretization. We cannot expect to resolve the details of a baroclinic wave that is observed maybe, but still we have the possibility here of things that change with height and that interact, the 2 levels interact with each other. But yeah, in principle you can go and say, oh no, I want to solve this problem now for 10 levels, and you solve it for 10 levels. I don't know, it's easily possible, but maybe yes. But then you can also try, okay, I want to solve this 3-dimensional problem immediately, and then you have to use more advanced mathematical methods to do that, but it can be done. One can gain some stability analysis also from the three-dimensional problem. But we have chosen this simple approach to baroclinic instability. So, what we want to do is, of course, we want to linearize our system again. Because even this three-dimensional system is nonlinear. And we don't know how to solve it easily. So we make the same assumption as before. But now we have the problem that we discussed last lecture, that we are actually looking for solutions that amplify. So really our solutions that we impose later on, where we control the amplitude, that may only be valid for a limited time, because then if the waves grow, in the end the linearization will not be true anymore. But this is what it is. We look for conditions that make the wave grow. And the essential trick is now, okay, we say again that our waves, that our solution is can be decomposed into a mean state that fulfills the original equation, plus a perturbation. And for the omega field, we assume that the mean vertical velocity in our domain is 0. This is a very reasonable assumption. It cannot be, the air cannot move up everywhere. It has to go down. So the mean vertical velocity is 0. So it's just determined by the perturbation vertical velocity. Instead, we allow a mean flow, and this is important now. We know intuitively already that we have to impose different mean flows in the two levels in order to get baroclinic instability, because it will be the mean thermal meridional temperature difference that is related to a change of wind with height through the thermal wind balance that governs the growth of our baroclinic waves. We will confirm this later. That's what baroclinic instability is about. We have to have a vertical shear of our mean flow, because that's related to the horizontal temperature gradient. Otherwise, we could only have barotropic instability. But here, baroclinic instability is the main source for growth. There's also barotropic instability. Barotropic instability is you have a strong jet flow that becomes unstable. We have jet flow in the atmosphere, and gives rise to smaller eddies. That's also the case, that can be the case. But very interestingly, what's happening on average is actually the opposite. The eddies, in terms of momentum, feed back, also in terms of energy. The eddies feed back kinetic energy to the mean flow. There's a very interesting feature of two-dimensional turbulence, which is not present in three-dimensional turbulence in general, where if you have a strong jet flow, then it will create smaller eddies and dissipate. In our three-dimensional turbulent case, we will show that later, it's a feature that these eddies that grow baroclinically will eventually feed back kinetic energy to the mean flow. It's part of the energy cycle. It's an interesting feature. So it's a real interesting problem. So if we make this assumption, we have made a small even simplification with respect to our Rossby waves that we have derived, because we assume now, for simplicity, that these waves are only propagating in zonal direction. So we linearize our equations, and the linearized equations look like this. It's very straightforward to do this. The operators guarantee that this Laplacian operators always guarantee that the advection term only contains these terms, and this x derivatives also here, and here we have only the prime quantities, and then the thermodynamic equation is essentially the same. So it's a very straightforward to linearize the nonlinear equations with a mean state that was given. And then we have to we make some more abbreviations. We want to define some kind of mean advection velocity, which is the mean velocity between the two levels. And we have something like a thermal, we define something like a thermal wind, a thermal advection velocity, which is the difference of the wind between the two levels. This is the ingredient, of course, the main ingredient for baroclinic instability. Whereas this is a kind of just the mean advection. Oh, also here we have expressed the velocity that should be defined at the level 2 in the thermodynamic equation by an average between the velocities in the two other levels. It's very straightforward to do this. Tedious, but straightforward. No problem. So then we can express the two velocities u1, the two velocities u1 and u2 we can express by either the mean velocity plus the thermal wind or the mean velocity minus the thermal wind, because if we add them, this u3 goes out. If we subtract them, then the u1 goes out. So this is just replacing. So this equation now looks like this with this other terminology. And it's also convenient to introduce now for the stream function perturbations what we call a mean stream function perturbation and a thermal mean stream function perturbation. So one is indicating again the mean field between the two levels, the other is a difference. So it gives us how does our stream function change between one level and the other. And it turns out to be convenient to do this. So we can either now add these two equations, the two vorticity equations at the two levels. If we add them, it's a way to get rid of omega altogether. So we add the two, we get rid of this here, and there's just one equation for the two levels, for the vorticities at the two levels. If we subtract them, we can do that also, and then we have to remove omega by the thermodynamic equation. Both is done. So the first equation here, which is still equivalent to the vorticity equation, is gained by adding the vorticity equation at the two levels. And the second one is gained by subtracting them, but replacing omega, the perturbation vertical velocity, by the thermodynamic equation. Therefore we get this lambda square in these equations, which is related to the stability of the atmosphere. So this is this is incorporating the thermodynamic equation, and this is just the vorticity equation. But it's very straightforward manipulation of the equations. So now we have removed, before we had three equations with three variables. Now we have removed the omega field completely. Omega is not present anymore. So we have two equations for two variables. Our two variables are psi m and psi t. So we should be able to solve this. We solve this, of course this is now a linear equation. We have linearized the equation. We make assumption that they behave wave-like. And then we know in the end that we can express any shape by superimposing as many waves needed to create any shape of our perturbations. But in order to gain insight in what is the dispersion relationship, we make just this assumption that we can find a solution by inserting these waves. And we know it's a linear equation with constant coefficients, so we are convinced that this will solve our problem. If we do that, we know what's happening. If we make this assumption, and these A and B are constant, then the advection term will always bring us down this IKC minus UM. We have done this already. Then the second derivative with respect to x bring us k square. And then sometimes we have a lambda square. And here's the third derivative. Sorry. Up here we have also the third derivative of the stream function. It comes down here. So that's straightforward to do. We divide by the wave itself, and we get a system for our two amplitudes A and B. And again, as before, we know that this has a solution. One solution is always that A and B is 0. But we are looking for these non-trivial solutions where we know that it can be found by determining that the determinant of this matrix applied to A and B is equal to 0. So this matrix is just the components we divide by I. So the good news is, in principle now here, no I appears. So there's no immediate instability visible. The instability will come later from some square root that we take. But the I, which could give us a grow or a decay, is not present in this version here. So the determinant of this is of course this multiplied by this minus this multiplied by this, which is this equation here. So we get a quadratic equation for our phase velocity. It's just simple algebra. So what we want to do is we want to solve this for the phase velocity, or for, let's say, phase velocity minus UM, because they always appear together. So we can solve it directly for C minus UM. It's a quadratic equation. We know how to solve this. So we can first divide by this term, for example. And then we get some other term here, and then we get some other term here. Then we have a form like C minus U m squared plus 2c minus UM times something. You know how to solve a quadratic equation. And the third term has to be like, is this addition, this beta or whatever it is, what we call it, has to be plus beta squared. We add that on both sides and we take the square root. And that gives us an equation for C minus UM. We know how to solve quadratic equations, right? Or you look it up in a formula. Anyway, what you get is C minus UM is equal to minus beta. That was the term that was remaining here that we have added. Minus beta k square plus lambda square divided by this, and then plus minus square root of delta, where square root of delta is this expression, where delta is this expression here. One thing we see already immediately, if the thermal wind is 0, there can be no imaginary solution. No part of the solution can be imaginary, because this is 0. If this is 0, the solution is real. So we are back to our barotropic case in principle. A little bit more complicated, but essentially we are back to that case. There can be no growth, and this is intuitively the correct result. We need to have a vertical wind shear, which corresponds to a meridianal temperature shear change. So we know immediately now if this becomes negative, then we have an imaginary part. That's an interesting case. And then we also know that one solution has to grow, because we always have plus and minus in the solution. So even if one solution decays, the other solution will always grow. So one of the two solutions will grow when this becomes imaginary. So there will be exponential growth. Now, one interesting case is, what happens now if in reality the thermal wind is 0, which could happen. We can make this assumption here. We should go back to our Rossby waves. Indeed, we go back to our Rossby waves. We still have two solutions. And the two solutions, one is in fact our barotropic Rossby wave speed, where instead of having k square plus L square, in this case, in this solution, we have only assumed zonal wave propagation, so we have only k square. That's this here. But the other solution looks almost like it, still real, but modified by this, by the stability. So we get an expression that looks a little bit like our waves in the ocean that were modified by the fact that we could have a perturbation of the height. Both are due to the fact that we allow the system to have vertical velocity. We have not set to 0 the vertical velocity, which is different from the case that we have looked at before. We have only imposed here now that the waves cannot grow. They can have vertical velocity, but without growing. And then yes, there are these two solutions. Some modification of our case already, because we are permitting the waves to have a vertical structure in principle, which is different from what we have assumed before. So the phase speed with respect to the mean flow would be reduced in this case. Now the interesting consideration that we have to do is we say, okay, it's kind of delta looks difficult, the solutions look difficult, but one trick would be we look at the curve delta is equal to 0, which is just the point, how does it, this means our waves just do not grow. They are just at the limit of the instability. But if delta is equal to 0, that means if we change it a little bit, it could be positive or negative. If it's negative, then our waves grow. So the line is what we call marginally or neutral curve, marginally stable line, is identified by delta is equal to 0. So we just, from this complicated equation here, for the phase velocity, we just consider the case, we set delta here to 0 and see what kind of relationship between wave numbers and thermal wind do we get from that. What is this critical line? And that can be expressed then in this way. And you can solve, this is again a quadratic equation. And you can solve this because it's quadratic for the wave number, because you see it contains k square here, k square here, and k square here. So if you multiply this up, it goes up to k to the power of 8. Then in the end, if you solve that and take the square root again, it's again a quadratic equation, so you get again such a kind of expression. Again, quite complicated. So this is a relation between thermal wind and wave number just at the critical line, just when waves are neutral. And you can draw this in a diagram. I've done this in MATLAB actually. And so this is the neutral curve. So waves within this, they do grow. Positive is not true. Waves within this hashed region here are unstable and do grow. So on this axis you see the scale wave number. It's a dimensionless wave number. And on this scale you see a dimensionless stability parameter, which is the proportional to the thermal wind. So we know that if the thermal wind is small, then all waves are stable, which is intuitively clear. If the thermal wind becomes larger, more waves become unstable. And so it's interesting actually to say, okay, if I start from a stable case, let's say we start from very small thermal wind, and now I make the thermal wind grow. What is the first wavelength that becomes unstable given thermal wind? When does the wave become unstable? To solve this problem, in principle, we have to turn this up and calculate the derivative du by dk and set that derivative to 0. But we can do it kind of numerically if you want by posing this here. In fact, this is the case if this is this value is equal to 1. Yes, you can either solve this problem by calculating a curve for u dependence of k and then calculating du by dk and setting that to 0, or kind of to do this trick numerically if you want. And the conclusion is that the most unstable waves for a given u, the first unstable wave for a given u, appear when k square is equal to square root of 2 times lambda square. Now lambda square is our typical stability parameter for the atmosphere. We have given some number previously. So this now has we can calculate what this number is. And it turns out that this number, if we take the square root of this, it's around 4,000 kilometers. And again, if we look on a weather map, most of the waves that we see, most of the baroclinic waves that grow, are about this wavelength of 4,000 kilometers. So that would justify, in some sense, our approach. The final result is kind of consistent with what we find on a daily weather map. That these perturbations are the ones that typically show typically growth. Very important property, baroclinic instability. We will show later in if we consider the energetics, and we have seen this probably already in our first lecture, what these waves in reality do is they transport warm air to the north and cold air to the south. So by taking energy away from the mean state, they are eroding the meridional temperature gradient. That's if you want, their aim. They're eroding the meridional temperature gradient, extract energy by that from the mean state, and cause energy as a perturbation energy. However, as I mentioned before, we have to be careful because this energy is taken from the thermal mean energy and is now in these waves immediately, once they are created, they are perturbation thermal energy, but they immediately create kinetic energy. Our stream function solution is kinetic energy, so that's kinetic energy. And in the end, it turns out that these waves also transport back this perturbation kinetic energy to the mean kinetic energy. But they have to do it differently. They cannot create back the temperature, the vertical wind shear. When they give this energy back to the mean flow, that energy will be given back as a barotropic energy. So the mean flow will gain kinetic energy from these perturbations, from these baroclinic waves, but in a way, in the sense that the energy is given back in a barotropic way. It's a very interesting feature of our extratropical flow. So we have this possibility, and we will discuss this in more details. So yeah, in principle, there's an exercise, but I don't want to do that because it's not so exciting. It's what happens if we add friction, a simple friction parameterization to our system. But I don't think this is very useful. It's just tedious to do. So you are lucky there will be no exercise. You can try to repeat the exercises who didn't do them from the last lecture. So far we have treated extratropical systems, extratropical waves. Next lecture we will go to the tropics. And the reason, in principle, we could say we could have solved the problem together. Why distinguishing? But again, it's easier to distinguish it. In principle, the equations that we have solved so far, they also contain the tropics. But remember, when we have assumed f naught to be constant, we have assumed it was fixed in some mid-latitudes. The problem with an f naught, that if we go then to the equator, the f naught at the equator is 0. In fact, we will make this assumption in the next lecture. We will actually place ourselves exactly on the equator, where the f naught is 0, and then the Coriolis parameter dependence is just a linear dependence without constant coefficient on the meridional direction. And that will make a new wave type appear, which we will see, which are the Kelvin waves at the equator, and some other interesting Rossby inertia waves that we also see at the equator. So we will try to solve the system for the equator, and that will give us very interesting trapped waves. Waves will be trapped close to the equator. Again, we will use a very much simplified system, because we will have again the problem that the real atmosphere is of course compressible and very complicated. But to solve the system, we will again assume that our waves are very shallow, and we will see if the solution for these waves then we can apply to the real world. But yeah, we always have to keep into mind that we have simplified the system a lot to find our wave solutions. Yeah, so the equatorial waves will be a very interesting ingredient also later on, to understand the ENSO response, the response to ENSO forcing in the tropics. And so that is what we discuss in the next lecture. So the extratropical part for the time being is done. Now we will consider more the tropical waves and the tropical dynamics. Later on we will go back to how tropics and extratropics interact, but for the time being we keep it separate.
May I ask a question?
Yes.
I can't really imagine how this paratropic or paraclinic abilities are in reality. So apart from the dispersion relationship, paraclinic instability has a vertical structure, but then what we see is the same eddy or something like that, a perturbation.
Yes, that's a very good question. Yes, they have an interesting vertical structure actually. So it turns out that in order, one can do this probably even by inserting the dispersion relationship back into the original equations. You can probably turn that out. So it turns out that if we have a low pressure system at the surface, let's say this is the lines, in order to be baroclinic, this has to have a tilt with height. So usually at upper levels the low pressure will be to the west. So the upper level is the low pressure. Will be here. The reason is, how can I say the reason is? This is actually a condition for a baroclinic wave to grow. I don't know at the moment. This is a necessary if you insert kind of these the solution from the phase velocity that we have found back into our equation. You will see that the perturbations at the two levels, they have to be tilted like this in order for the wave to grow. And for the ridge, it's a similar situation. So yes, this has to be the case. Waves have to be tilted in the vertical direction in order for them to grow. And it turns out that the growing wave, when there is a trough at upper levels, the low pressure will always be to the east at lower levels. And you can show that the rising motion, in fact, the rising motion, so W positive, will be always on this side, and that makes the surface cyclone grow actually. Always on this side of a moving trough. Yes, so that's a necessary ingredient for a baroclinic wave. And you can show this structure by taking the dispersion relationship and inserting that back into the equation in the system for A and B. Then you can see how the structure of the waves look like. Yeah, we don't do this. One could even do an energetics now, having the linear equation set of equations. We could try to calculate the energy of this, and we would see, okay, there's this energy conversion from the mean reservoir of thermal energy that goes into the kinetic energy of the perturbations. The way back we cannot prescribe it here. But yes, there's much more to it. So yes, that's the case. Waves have to be tilted with height in order to be baroclinically unstable. And that comes out if we insert the solutions back into the mean state.
In
This will be the typical
barotropic case, we would have two lows.
For the barotropic case, they would be one over the other, and then they don't grow anymore. Yes, that's the typical structure. Yes, there can be done much more for, we could call this dynamic metrology, in order to understand also, for example, what is this vertical velocity here. Okay, this could be also expressed by omega, of course. There's an equation called omega equation, a tendency equation for the prognostic equation for the vertical velocity that we can derive using the thermodynamic equation, of course. And that will show us that this position with respect to the upper level trough is always favorable for positive vertical velocity if the trough is moving in that direction. Yes, that can be derived from an additional equation that we haven't studied. We have only studied more carefully the vorticity equation, but we haven't studied what is called in dynamic metrology the omega equation, which is an alternative equation which can be derived using the thermodynamic equation. If you have that equation, you can show that there will be positive vertical velocity on this side here due to warm advection and also vorticity advection. There are several components that can create positive vertical velocity. And this position kind of fulfills all criterions because there's positive vorticity advection and there's positive temperature advection that both would lead to a pressure decrease on low level pressure decrease on this side of an upper level trough. Yes, there's much more to it. And things can actually be much more complicated because in reality, maybe there are even what we call frontal systems. You see them if you look on a weather map. Sometimes, we are here thinking everything is wavy and smooth, but in reality there may be very, very small transition regions from a warm air mass to a cold air mass. And you really see this on a weather map. If you look on this famous windy page that Adrian sometimes shows. This is really, really, really small transition regions of maybe 100 kilometers where most of the gradients are located. So much more complicated than imagining smooth, wavy behavior. But those features we cannot describe using theory, only these basic features. Yeah, no, this is very important. One way to get positive vertical velocity is to study the relative position of upper level trough and low level trough. And with respect to an upper level trough, you can show by using the omega equation that this is a very favorable occasion for low pressures to grow because of both warm advection and vorticity advection that act together to make the perturbation at low levels grow. Yeah, then it turns out at some point, if the life cycle of the cyclone goes to an end, then they become barotropic. And the omega equation would tell us that once they have reached this state, there is no vorticity advection anymore, relative vorticity advection, and no thermal advection anymore that can make the cyclone grow. Yes, thank you. It can be much more complicated. We have just touched on the basic ingredient of the baroclinic instability. But yeah, it can be discussed in much more details.
May I ask something about assignment number 3?
This last one, the last from the last week, from Friday. Yeah.
Certainly the question seems to have three in one. There is this one of deriving the velocity, then deriving the equation, and the translation. Certainly here, you have not mentioned that the h prime varies in t. If you actually look at this equation, it has the x component and the perturbation also has an x component. Therefore,
yes.
You cannot do anything.
This comes from the right hand side. If you insert this on the right hand side, yes, this one here.
If you substitute the differential with the capital H goes away because it is the mean.
Right. So you only maintain the perturbation.
Yeah. But the perturbation varies in T and also in Q.
Okay, but there's no mean flow. If we had used the mean flow, then there would be again some kind of Doppler shift that we have to take into account. But we have said U bar and U bar is equal to 0 for this case. Therefore, the only term that remains after linearization of the total derivative. So if we linearize the total derivative, it would be U bar plus U primed d by dx, in this case only h primed, plus the v bar plus v primed d by dy h prime plus dh prime by dt. These terms were 0 because of our assumption of the mean state velocities to be 0. These we we treat as nonlinear terms. So we assume that we can control the amplitude again, that they are small with respect to the linear term. So the only linear term in that case remaining is this one here. Yes. And we can evaluate, and this can be used then on the left-hand side where we have already perturbations of the height that we are dealing with. We cannot use the du prime by dx, the divergence form, because this cannot be expressed by the stream function at all. So these are the ageostrophic velocities so we cannot make use of this. Therefore, we have to use the total derivative of the height field on the right-hand side of the vorticity equation. And the linearized version gives only this term. Okay?
Although the question said from equation set 11, the derivation must not be made from equation 11. But is there a direct link between absolute vorticity and the height H? Because if, for example, you run that vorticity equation of ddt of absolute vorticity, E plus an F is equal to the same equation on the right-hand side. Is there a direct relationship between the two?
The vorticity is related to the height of our system. Sometimes we have assumed that height perturbation we can ignore when we calculate our Rossby waves in the standard way. But for the ocean case, it turns out we can take this small height perturbation into account, and maybe for the ocean it gives an irrelevant contribution. So yes, there is a relationship between the vorticity and the height perturbation, because the height field in fact acts as a stream function for our vorticity field. So yes, there is a relationship. Yeah, and it's in principle more correct to include the fact that we have in our barotropic model at least a height perturbation. It's correct to include this into the dispersion relationship in the end, and not to ignore it as we did for the atmospheric Rossby waves, where we have set the right-hand side of the equation to 0.
If there is really a direct relationship, then it is possible that one could use equation 11 and then use the beta approximation of f0 plus beta y, right?
Equation 11 plus? Yes.
So if there is a relation, then if I substitute this with the h, means this will become f0 plus a beta y.
Right.
And
But we have to replace this again by the height difference. No, we have said that because the divergence is expressed by the ageostrophic velocity component, which cannot be directly expressed by the stream function. So we replace this by the h by dt again. Okay.
then the beta y.
Oh, the beta comes from this one here. Beta df by the df by dt is just v df by dy, so beta times v, and v we can express by dh by dx. So it comes from this side of the equation. Do you see that? Yes. Yes. And so And then in the linearized version, you can express d prime by dh by dx. dh prime by dx. Therefore, we get in the final equation here dh prime by dx times beta. It comes from this term here. Yes. So the only difference with respect to the Rossby waves that we have dealt with before is that we take into account on the right-hand side a divergence, the divergence effect that can be expressed by the height perturbation of our system. Okay.
Yeah, thank you. Really helpful.
Here.
This
Yes.
nice.
Should we leave this here to scan a solid earth field pool? They are pretty, they are really lucky. Yes, it's not very mathematical.
Cool.
Their courses this semester is not very mathematical.
Cool for